Okay, so last time we learned about axiom of power set, which told us that for every set there exists a set which contains all subsets of this original set, and we introduced with that axiom we have introduced 6 axioms, and you can check that those 6 axioms are not sufficient to do mathematics. For once we can prove the existence of an infinite set. So we're going to introduce more axioms, but before that we're going to see what we can do with the axioms we've introduced so far. So these axioms are supposed to be a foundation of mathematics. So what are the most common objects in mathematics? What do you use most? Functions. So we're going to end according to our interpretation, everything in the universe of mathematical objects should be sets if we're working with ZFC axiom. So we should somehow define functions as sets. Okay? So in order to do that, we're going to first introduce the notion of a relation. Now, a set R is a relation if it consists of ordered pairs. Okay? Any set whose elements are ordered pairs is called a relation. In other words, if for every element of R there exists yz such that this element is the ordered pair yz. What was the set theoretic definition of this ordered pair? This was the following set. Okay? So we just made a definition. A set is called a relation if this holds. Now, let's introduce more definitions. Most of today's lecture is going to be spent with introducing definitions. We're not going to prove a theorem, maybe 1 or 2 theorems, okay? We're just going to introduce some terminology. Okay. So we defined what it means for a set to be a relation. So let R be a relation. We define its domain and range to be the following sets. The domain of R is the set of all x such that there exists some y such that the ordered pair xy belongs to R. Okay? And the range of R is the dual notion. It's the set of all y such that there exists some x such that xy belongs to R. Now, why are these sets? Can you prove that these objects are sets using the axioms we introduced so far? Yes. I would leave this as an exercise. Just remember the definition of an ordered pair. So use the axiom of union and the axiom of separation to show that these are actually sets. Okay? You see, at the beginning, I was actually explaining in detail how each set I write on the board is actually a set, like using the axioms. But as we progress, I'm going to stop doing this because it's going to take too much time, and after some time, you'll get so used to it that you'll be able to do it on your own. So try to prove that these are sets using axiom of union and separation, okay? Okay. So more definitions. Let me use this. Let A, B be sets and R be a relation. So we have two sets and a relation. We define the image of A under this relation R, and the inverse image of B under R to be the following sets respectively. Okay? So I'm going to define the image of a set under a relation and the inverse image of a set under a relation. Okay, the image of this set under this relation R is a set of all y such that there exists some x so that the ordered pair xy belongs to R. And the inverse image, which is denoted like this, is a set of all x such that there exists some y and b such that xy belongs to R. Now what are these? I defined the notion, but I didn't explain what this is. A relation is, it's supposed to be thought as a rule which relates objects, as the name suggests, okay? It relates certain objects to each other. Given two objects, either they are related under this relation or they're not. If this has some special properties, we're going to call it a function. But in general, a relation is supposed to just relate certain objects to each other. The domain of a relation is the set from which it relates objects. And the range of a relation is the set to which it relates objects. And the image and inverse image of sets under relation R is defined as follows. The image of a set under this relation R is a set of all sets that are related to by R using some element of A. And the inverse image is defined as the set of all sets which are related to some object in Y, is in B, okay? So this is the notation we use for inverse image, just like the usual inverse image notation for functions, except we're just introducing it for more general objects. So let me write down an exercise. Let A be sets. This is for those who have not reviewed Math 100, okay? Even though I told you to do so. Consider the following relation. So find the domain of this relation R. Let's name this R. And find the range of R and let's say find the image of this set and the inverse image of the singleton B, okay? Do this on your own time. This is really easy. Just use the definitions. So we introduced the image and the inverse image of a set under a certain relation. Let's talk about inverse relations. So let R be a relation. The inverse relation R inverse is the set, this is the set of all ordered pairs BA such that AB belongs to R, okay? So you basically pick all ordered pairs in R and flip their components. Now, why does it matter that we flip these components? Because these are ordered pairs, not unordered pairs. The order actually matters. And relations are supposed to relate objects, but we have a certain rule, whatever that is, but this rule does not have to have any properties. Like it can relate to some object to this, it can relate this object to this object, but not the other way around. So sometimes we want to go back, we want to go in the other direction. If some object is related to some other object, we want to somehow come back, and for that we use the inverse relation. Now, as you can see, I used these symbols to denote two different objects. Over here, I used it to denote the inverse image of a set under a relation, and over here, I used this guy for the inverse relation. So when I write this down, what are you going to understand? You're going to understand the image of B under the inverse relation, or the inverse image of B under the relation R. Which one? It turns out that it doesn't matter. This is why I can actually do this, use this notation for both notions. So let R be a relation and A be a set. Then the image of A under R is the same as the inverse image of, the image of A under R inverse is the same as the inverse image of A under R, okay? Now I'm not going to prove this. This is really easy. You can do this on your own time. So let me do the following. Proof exercise. Just use the definitions. It's just going to work out. The point is, using this notation makes sense for both notions, both the inverse relation, for both the notion of inverse relation and the notion of inverse image. So let's introduce more definitions, but before that, let's make an important definition. Or should I do that? I'm going to erase this word. Okay. Let A and B be sets. Now, I want to form a set of all ordered pairs where the first component comes from A and the second component comes from B. Why is this a set? Like, why does the set exist? You probably think that you can use the axiom of separation to form this, and it is true, except like this is your formula, but when you need to use axiom of separation, you need a formula and you need a set from which you pick the elements which satisfy the property you chose at the beginning. So in this case, the set we're going to choose these elements from is the following: power set of A union B. You can double check that this set, which is the set of the singleton x and the doubleton xy, belongs to the power set of the union. If A and B are sets, this is a set, the power set of that set is a set, this is a set. I'm picking all the elements of a set which satisfy a certain property. So by axiom of separation, this is a set. This set is defined as, it's called the Cartesian product. The Cartesian product of A and B is the set of all ordered pairs such that the first component comes from A and the second component comes from B. Okay? So let's keep this on board and introduce more terminology. Where's the purple chalk? Oh, it's over there. Okay. Now when you pick up a mathematics book and read something regarding relations, you will see the phrase blah blah is a relation from something to something. So let's understand what those words mean. For those who arrived late, today most of today's lecture is going to be devoted to introducing terminology. We're only going to prove maybe one or two theorems. So let A and B be sets. A relation R is said to be from A to B if the domain of this relation is a subset of A and the range of this relation is a subset of B. Okay? So a relation from some set to some other set is a relation where the domain is a subset of the first set and the range is a subset of the second set. Okay? And a relation R is said to be defined on a set A. When I use the phrase relation on a set, I mean a relation whose domain and range are subsets of the same set. So this is a relation R is said to be defined on a set A if well, actually, do I want? No, I don't want that. Okay? So, you can double check that these two properties is the same as saying R is a subset of this Cartesian product, and you can double check that this property is the same as saying R is a subset of this Cartesian product. Okay? So we introduced more terminologies. Let's give a name to these guys. Well, should I give them a name? Well, when R is a function, these are usually called domain and codomain, and those definitions can be extended to relations actually, but let's not take that road. Let's not actually name those. I changed my mind. Okay. Now a notion which you're familiar with, but have not probably seen before. You're familiar with the word, but you're not familiar with this word being used for relations. Let R and S be two relations. The composition of R and S maybe I should say with, because the order is going to matter. If I say and, you're going to think that the order doesn't matter. The composition of R with S is the set of all ordered pairs X Z such that there exists Y so that XY is in S and YZ is an R. Okay. So this is the usual notion of composition you know, except it's defined for relations, not just functions. So what does it do? Okay. Let's say I have a relation from some set A to some set B, and let's call this relation R. R is a subset of this Cartesian product. No, let's call this S. And let's say that I have another relation from B to C, which is called R. Now, a relation is simply a set of ordered pairs, but I can just intuitively think of relations as rules that assign objects of this set to objects of that set. So maybe the picture looks like this, okay? Let me put some elements over here. And this is not related to anything, or yeah. Let's do that. And let's relate the elements of this set to elements in this set. Okay, so think of these purple arrows as a relation from A to B. This object is related to these two, this object is related to these three, and this object is related to that object. And the orange arrows represent another relation. Now the composition is, let's read the definition. It's supposed to be the set of ordered pairs X, Z such that there exists some Y so that XY is related by X and Y are related to each other by S, and Y and Z are related to each other by R. So this green arrows I'm about to write down are supposed to represent the composition. Well, you see, I can ask the following question: is this pair, the pair consisting of this element and this element, in the composition? If so, if that were the case, there would be some element Y such that I could go from this element to to that Y, and from that Y I could come back here. But there's no such element as far as I can see, so these two are not related. However, these two are related because there exists some element in here such that these two are related by S and these two are related by R. Okay? So basically, an object here is related to an object here if you can just follow the arrows and reach from this guy to that guy. So this is just like the usual notion of composition for functions, except you're doing this with relations. So let's double check that. Let me draw the correct picture. From here you can go there, so these two are related. These two are not related. From here you can go there by following this path, so these two are related. From here you can go to this guy, so these two are related. From here you can go, no, you cannot go there, so they are not related. From here you cannot go there, they're not related. So from this you can't really go anywhere. So the composition consists of 4 ordered pairs, okay? As you can see, there are 4 green arrows. So that's the composition. For some reason, I just spent too much time explaining a notion which you're already familiar with.
Yeah.
Yes?
What's the difference between like relation and function? They look similar. Relation and function.
Well, we haven't introduced a function. We haven't introduced the notion of a function. A relation is a set of ordered pairs. Okay, what's your question again? Like the difference between function and relation.
Yes.
A function and their relation. What's the function?
A function also gets input and makes output.
Sure, but what is a function?
Hmm?
What's a function?
Well, it's an operation which takes input and
Sure.
makes output. And during other classes.
But what does that mean? Takes an input and produces an output.
Like between 2 sets, it's also like a relation.
Sure.
So.
But if why does it produce one output when given a single input? Because that's how it's defined. So that's the difference.
Yes. I see.
Basically, you'll see the difference when I define it. I just introduced Thor, and you were asking what's the difference between Hulk and Thor. But I haven't introduced Hulk yet. Okay? When I introduce the function, you'll directly see the difference. Okay. So let me write down some exercises. Oh, I haven't finished erasing the board. When I define the notion of a function, I'll start with the following phrase. A function is a relation satisfying blah blah. There will be a property, and that will be the only difference. Okay? So let R and S be relations. Now, prove the following. Let me give you 3 relations. Prove the following 2 identities. The inverse relation of a composition is the same as the composition of the inverse relations, except you flip the order. Just like the notion of composition for functions. Basically, the notion of composition that you knew is actually defined for relations in general, not just functions. And it satisfies the same properties. For example, it is true that if you have more than 2 relations, it really doesn't matter how you compose these as long as you try to compose them in the same order. In other words, the composition is associative. Okay, prove those 2 identities from the definition of composition. Okay. How many minutes do I have? 15. 2 important relations. Let A be a set. The identity relation which is noted by delta most of the time. The identity relation delta sub A, it means that it's the identity relation on A is the relation consisting of all ordered pairs XX such that X comes from A. Okay, so all the things in A are related to themselves, but they're related to only themselves. This is the same as the usual identity function. Everything is sent to itself, except we don't really know what a function is at the moment. We will learn in a second. And now this one, you know, because you know the identity function. This one is gonna look weird when you see it. But you should get used to this because we're going to define ordinals using this relation. The membership relation, which is denoted like this, epsilon sub A, it is following relation. Now this relation is defined on A, meaning that its components are coming from A. And you relate some object to some other object if and only if this first object is a member of the second object. This is why it's called the membership relation. It tests whether two objects in the set A are related or they're members of each other or not. Okay? So I'm picking all elements of A. If X is a member of Y, I'm relating them. This is the membership relation. And we're going to use this a lot, as I said. Okay. So we did that. I think we can start talking about functions. Now I'm introducing the Hulk so that you can ask the difference. And the difference is that Hulk smashes, Thor uses his hammer. Okay, so a relation relates two objects. But if you read the definition, it can relate everything to each other. You can pick a set and you can just relate everything on that set to each other, okay? Which wouldn't really makes sense, but it's still a relation. Now, in mathematics, most of the time we're interested in special relations. What kind of relations? Now, a relation is supposed to be a rule that relates something to something else, but sometimes you want this relation to be, in a sense, uniquely defined. What do I mean? You want, let me use your words, when given an input, you want to produce a single output. Those relations are called functions. So let me define a function. A relation R is said to be a function if, now, I was planning to write down some English phrase, then write it in informal logic, but I'm going to skip the English phrase and I'm going to write down the definition using logical symbols. A relation is said to be a function if it satisfies this property. What does this say? It says that if an object is related to y and z under this relation R, then these objects are really the same. In other words, any object which is related to something by R is actually related to a unique object, if it is related at all. Okay? So let's use these Venn diagrams. A relation is a function if this does not happen. If a single object is not mapped to two different objects. Now this notion sorry, let's not do this. This property is sometimes called being well defined, okay? When you say a relation is well defined, you mean this, okay? Let's put this in parentheses. Okay? So, a relation being well defined simply means the following. It does not relate an object to multiple objects. Okay? So, this is simply the difference. Okay. Now, let's introduce more terminology. Okay, what's the example of a function? Construct a function using the axioms you learned so far. Okay, you know examples of functions. I know, like identity relation is a function, it's the identity function, but what else? Now, you learned functions as rules that take an input and produces some output, like you described. But for this course, functions are going to be special kinds of relations. So you have to stick to this terminology. Why am I emphasizing this? Is this a function? Empty set. Why? First of all, is empty set a relation? Yes, because every member of empty set is an ordered pair. If you try to prove otherwise, you'll have to find some member of empty set which is not an ordered pair, but you cannot find any, so every member of empty set is an ordered pair. This statement is vacuously true. It's simply true because there are no members. Now, does empty set satisfy this statement? If I put empty set here, is this satisfied? Well, nothing is a member of empty set, so this part of the statement is false. Well, a statement of the form P implies Q is true if P is false, so this statement is simply true. So this is a function. This is why I'm saying, like, you should not think of functions in the conventional way, like rules assigning certain things to certain other things. Well, what does this do? It relates, it doesn't relate anything to something, okay? Nevertheless, it is a function, okay? So a function is a special kind of relation. It's a well-defined relation. In other words, a well-defined relation is a function. Okay, I have 8 minutes. Let me introduce more terminology. I'm not even going to be able to prove anything. So today is basically the definition day. I just kept writing definitions, and it seems that we're going to finish this lecture like that. So, let R be a relation and ABB sets. Then, well, R is said to be a function from A to B if, first of all, it should be a function. And the domain of R should be a subset of A. Sorry. It should be exactly A, and the range should be a subset of B. Okay, so when you learn, in 111 you actually learned the theoretic definition of function, except it was probably introduced in the following form: a function from blah blah to blah blah. And some set theory books do it like that, but the book I used to prepare my notes didn't do that. Yes, simply said that a function is a set of ordered pairs satisfying this. But in practice, we talk about functions from something to something, so let's define that. A relation is said to be a function from A to B if okay, the first requirement is that this relation should be a function, because we're defining what does it mean for a relation to be a function from something to something. And the other requirement is the following: the domain should be all of A, the range should be a subset of the second set B. In this case, you call this a function from A to B. Okay? More definitions. Okay, this is the boring part of the course, okay? I'm just introducing definitions, but it's going to be fun in 2 weeks, okay? Don't worry. Let's introduce a notation. Let's say that R is a relation and A, B, B sets. If R relates A to B, then we shall write R of A equals B, okay? We're going to use the usual function notation that you know. But we are actually using it for relations in general, okay? If A is related to B under R, then we write this. Definition. For some reason I switched to orange. Let f be a function from f be a function. Then f is said to be okay, let's make this a function from A to B, okay? Sorry for this. Then f is said to be injective or one-to-one, surjective or onto, and bijective if the following happens. Injective simply means that the inverse relation of this function is well defined. In other words, it is not the case that two different guys in the domain are mapped, are related to the same thing. Okay? Okay. So for all x for all y, if f(x) equals fy, then x should be y. This is the same as saying that the inverse relation of f is well defined. It's called surjective if, okay, I'm going to write for all x and y here, and I'm going to write this. For all y in B, there exists x and a such that f of x equals y. That is, the range is all of B. It's called bijective if it is injective and surjective. Okay? And another way of stating this is, as I said, writing the following: f inverse is well defined. Okay? So I have 1 minute. Let me assign a little exercise. Again, there's nothing conceptually difficult here. This is just to make sure that you understand these definitions and you're able to use these. Now, if you read this definition, you'll see that this property has nothing to do with A and B. Okay, it really doesn't depend on, oh, it somehow depends on A, but it actually doesn't depend on these two, okay? But this property, it depends on A and B. More importantly, it depends on B, okay? When you talk about injectivity, to which set you go is not important, but when you talk about surjectivity, it does. So show the following. Show that empty set is a bijective function from empty set to empty set, but not a surjective function from empty set to a singleton empty set. Okay? So empty set satisfies that property over there, and we just saw that, so it means that this is a function. Now, is it a bijective function or a surjective function? Asking these does not make sense as is, because you have to specify a domain and a codomain. I haven't defined those, but I will write it down in a second. So you can ask whether something is a bijective function from something to something else, and I'm asking this. Is the empty set, well, I'm actually asking you to prove it. Prove that empty set is a bijective function from empty set to itself, and it's not a surjective function from this set to this set. Okay? And let me finally define domain and codomain over here, which I should have done like 5 minutes ago. Let me make an addition to this definition. In this case, the set A is called domain of R, and the set B is called the codomain. Okay? So, that's that. And we are on, if you're following the lecture from notes, we are on like page 11. Soon we're going to start talking about generalized Cartesian products, and we're going to introduce the axiom of choice. And I'm going to solve interesting puzzles, fun puzzles in class. But in order to do all these, well, okay, I don't think anything to do in order to do all these, but in order for you to follow all these, you should know all these definitions by heart, okay? So when I talk about a well-defined relation, you should just look, you should not simply stare at the board without understanding it. I know that you know most of these definitions, just make sure that you review them, okay? So, I will see you on Thursday, okay?